हेलो मैम।
या
मैम गुड इवनिंग मैम।
हाँ, गुड इवनिंग।
मैम आप लास्ट क्लास में बोल रहे थे कि कोई पीडीएफ भेजेंगे और एक।
अच्छा, कल कल का ना?
हाँ मैडम, पहले तो दो पीडीएफ भेजे थे।
हाँ,
मैंने
कल
आपको
का
मैसेज
और
किया
आज
था
का।
पर।
हाँ, कल का और आज
हाँ
का मैं खत्म होने के बाद मुझे उसको पीडीएफ में कन्वर्ट करके भेजना है, तो मेरे पीसी में वो नहीं है, तो मैं दूसरे पीसी में करती हूँ। तो थोड़ा टाइम
हाँ ठीक है
लगेगा।
मैम।
ठीक है। नहीं,
ठीक है
कर
मैम ठीक।
सकती हूँ मेरे पीसी में, लेकिन मैं वो ऑनलाइन नहीं करती हूँ। तो मैं भेज
अच्छा
दूंगी। नो प्रॉब्लम। और क्वेश्चंस मिला
ठीक
क्या?
ठीक है। हाँ मैम, थोड़ा वो ये कर रहा था बाकी अब तो नहीं मिला।
अच्छा अच्छा, वही लास्ट ईयर के सारे क्वेश्चंस अवेलेबल हैं। ये देखो, मैं एक मिनट मैं करती हूँ, देख। अभी देखो, शेयर कर रही हूँ। ठीक है। तो ये दिख रहा है। शेयर की हूँ जो स्क्रीन इंदिरा गांधी आई इग्नू का, वो स्क्रीन दिख रहा है।
यस मैम।
हाँ।
यस मैम।
तो इसमें देखो, नीचे है दिसंबर 2024, बाकी सब अवेलेबल नहीं हो रहा है। जहाँ दिसंबर 2024 है उसको क्लिक करना। ठीक है, उसमें बहुत सारा क्वेश्चंस है। तो इसी में क्या करना, जस्ट अ मिनट, वो बफर हो रहा है। हाँ, इसमें एक सर्च बटन है। हाँ, वहाँ पे MCH करके डाल दो। जो तुम्हारे सारे ये है आ गया। तो उसमें से तुम्हारा MCH 011 से शायद शुरू है ना? MCH 011 होगा।
यस मैम।
हाँ, उधर डाउनलोड कर लेना। ठीक है, ये डाउनलोड करोगे तो जैसे कि तुम्हारा इनऑर्गेनिक केमिस्ट्री का पेपर है, इनऑर्गेनिक केमिस्ट्री का। ठीक है, क्वेश्चन पेपर आ गया इनऑर्गेनिक। वो लास्ट ईयर का ही है। तो इसमें तुमको सारा मिल जाएगा, 11 12 13 14 15 16 जितना भी तुम्हारे पेपर्स हैं, वो सबका तुमको लास्ट ईयर के क्वेश्चन पेपर मुझे मतलब उसी में से आ जाएगा। ठीक है ना? वो कुछ नहीं, इग्नू में जाना, वहां पे डाउनलोड्स करके है। उधर तुम क्वेश्चन पेपर में क्लिक करो। तो ट्वेंटी ट्वेंटी
मैम
फोर के।
डायरेक्ट प्रीवियस ईयर क्वेश्चन मारना है क्या?
हाँ, प्रीवियस ईयर क्वेश्चन भी मारो, जैसे भी करो। गूगल में मैंने तो सिर्फ गूगल में डाला था प्रीवियस ईयर इग्नू क्वेश्चन पेपर्स। तो ये वाला आ गया। नहीं तो कभी कभी सिर्फ इग्नू का भी अगर जाते हो तुम साइट में देखते हैं, वो उधर भी हो सकता है। उधर भी स्टूडेंट सर्विसेज में चेक करो तो शायद मिलेगा, या किसी और में भी हो सकता है। नहीं, इसमें नहीं है। हाँ, इधर है। वो इग्नू के साइट में मेन पेज में जाना। ठीक है, उसमें स्टूडेंट सर्विसेज है, उधर डाउनलोड करके एक है। ठीक है, डाउनलोड में क्लिक करोगे तो इसी में ही है तुम्हारा प्रीवियस ईयर्स क्वेश्चन पेपर। इसी में एक है प्रीवियस ईयर्स क्वेश्चन पेपर दिसंबर 2024। तो उधर तुमको सब मिल जाएगा। ठीक है, वही सेम चीज़ है। तो इग्नू के साइट में जाके तुम्हारा स्टूडेंट सर्विसेज, उसी में डाउनलोड्स हैं। डाउनलोड में क्वेश्चन पेपर्स हैं। तो उधर से तुम चेक कर सकते हो। समझ में आया
ओके
ना?
ओके।
हम्म।
यस मैम।
इग्नू के होम पेज में ये तुम्हारा स्टूडेंट सर्विसेज है, उसी में क्लिक करोगे डाउनलोड आ जाएगा। ठीक है। तो यू कैन गेट प्रीवियस ईयर क्वेश्चंस। और बाकी क्वेश्चंस उतना एनेबल नहीं है। हाँ, दिख नहीं रहा है ऑनलाइन मुझे, या पता नहीं उससे पहले था भी नहीं था, वो मुझे पता नहीं है। ठीक है। ओके, आई थिंक
ठीक है मैम।
some have already joined. So good evening everyone. So we will start our today's class, which is most actually on reactive intermediates. So reactive intermediates, in the last class we have discussed already about carbocations and carbanions. In case of carbocations, we have in carbon we have three bonds attached to the carbon, and we have a positive charge. And in case of carbanions, we have a negative charge and three bonds are attached to it. And carbocations are actually trigonal planar because they are sp2 hybridized, and carbanions are actually pyramidal because they are your sp3 hybridized. So today we will discuss about other four reactive intermediates. One is your free radical intermediate, carbons, nitrins, and arynes. We will discuss one by one. So first one is your free radical. So free radical intermediate, it is like in this case also, in case of free radical, here you have three bond carbons and you have a uh, radical that is not a charged particle, it is a neutral particle, but this is a single electron, so that is known as your free radical. And in case of carbons, carbons are like double, carbon is bonded to two other groups or atoms, and you have a lone pair of electron on carbon. So this lone pair of electrons can be singlet or triplet, we will discuss about it. And similarly, in case of your nitrins, you have two lone pair of electrons. And arynes, in that we will deal with your benzynes, in which you have a carbon carbon triple bond, like your alkyne, you have arynes. So we will discuss one by one. So first one is our free radical as intermediates. So in case of this free radical intermediates, as you can see, the carbon is bonded to three other groups or atoms, and you have a single electron, that is a radical. So how these are generated? By this is being generated by your bond homolytic bond fission. The in case of your carbocation and carbanion, those were heterolytic bond fission, but in this case this is your homolytic bond fission, that is the bonded pair of electron is being equally distributed among the two atoms which share the bond. So there are many ways to generate these free radicals. One is by photolysis, that means in presence of light. For example, in this acetone, when we subject it to light, that generates a methyl free radical and an acyl free radical, which again undergoes decomposition to give carbon monoxide and methyl free radical. Similarly, so whenever we do this free radical mechanisms, we always use a fish hook arrow, that is one-sided arrow. And similarly, this ROCl, that or RONO, in presence of your light, that gives generates these free radicals. And mostly used are your diazides azides. Okay. So which in presence of your light, that gives you nitrogen as a leaving group and two free radicals. Similarly, these free radicals can be generated in thermal way, by thermal methods. That means by heating it. For example, when benzoyl peroxide is heated, that gives one benzoyl oxy radical. So this bond is being broken, like we have two electrons on this oxygen. So this peroxide bond is being broken to give you benzoyl oxy radical, which again loses one molecule of carbon dioxide, two molecules of yeah, it should be two molecules of carbon dioxide, and two phenyl radicals. Even this azobase isobutyronitrile, AIBN, this also undergoes actually this also undergo uh, homolytic cleavage to generate two free radicals, which again gives you nitrogen gas is generated, and it gives you a free radical intermediate, which again decomposes to form your uh, triphenyl methane free radical. So this benzoyl peroxide and azobase isobutyronitrile, or this is commonly known as your AIBN, these are actually used as initiators in polymerization reactions. Okay, because they initiate the reaction. So these are very widely used initiators. Next generation of free radicals are by redox reaction. In case of your redox reaction, as we know that redox reaction is a kind of oxidation and reduction reaction. It is a combination of oxidation and reduction. Never oxidation or reduction goes alone, they always go side by side. For example, in this case, ferrous, that is your Fe2 plus, is converted to Fe3 plus by losing one electron. And this electron, that means it is getting oxidized, and this OH group is being your reduced. So one electron, it transfers one electron to this one, so that that would form OH dot, and this bond pair of electron will go to this OH, generating OH minus. So this is a kind of redox reaction. Even with your this acetic anhydride in presence of your copper plus 1. So copper plus 1 gives one electron here, so that it generates say ArCO dot and ArCO minus. That is one carboxylate radical and carboxylate anion, and copper 2 plus. Copper is giving out one electron and itself getting oxidized and reducing your acetic anhydride to ArCO minus. Similarly, okay, so what is the fate of this acid, acetate radical? So this acetate ion, again at anode it loses one electron. Like electrolytically, when we do the electrolysis, it goes, as this is your anion, it goes to your anode, and there it loses one electron to generate your acetoxy radical, which again gets decarboxylated to give your alkyl free radical, which dimerize to give your product. So you might have seen it, your Kolb's electrolysis method in the preparation of your alkanes, Kolb's electrolytic method in the preparation of alkanes. Similarly, when magnesium, in presence of your iodide, that gives out one electron to form magnesium iodide, which on treatment with your acetophenone, that gives Mgi2 plus your anion radical, which again dimerizes to give you dianion. Dimerization means one of this kind that gets dimerized. We will come to the reaction part later on. So what is the structure and stability of your free radicals? So in case of your free radicals, as you can see, this carbon, this is your central carbon atom. This is bonded to three other groups. So, and it has another electron. So the number of electrons, total number of electrons in carbon is 4. And among these 3 electrons are used of in bonding. So one electron is remaining, and so as we can just consider three different, either this one electron will be in your hybrid orbital, or it can be in your pure p orbital. If we consider 3 electron and 1 electron as 4 pairs, then in that case it would be sp3. So if it is sp3 hybrid orbital, your electron would be in your sp3 hybrid orbital, because three bonds are being formed by the sigma bond overlapping of sp3 and sp3 or whatever group we are having there sp3. So we would have three bonds, and another sp3 hybrid orbital contains one electron. If this is not formed in your if that is not sp3 hybridized, it can also form your sp2 hybridized orbital, where all the three sp2 hybrid orbitals are used of in bonding, and you have a pure p orbital, which in which your electron resides. So in case of your sp2, whenever it has is forming a sp2 hybrid carbon or a center, then that should be a trigonal planar structure, and in this case it would be a pyramidal structure. So actually, if we just see, we can just depend on the substituent, actually, whether that contains sp2, this carbon is sp2 hybridized or this carbon is sp3 hybridized. It depends on these R groups. So if the R groups are bigger and bigger, so in that case actually they prefer to be in your sp2 hybridization, because in that case they would be as far away as possible. But if they are smaller, then they can be in your sp3 carbon. Actually, the EPR spectrum we will discuss about, that is your electron, that is yes, electron spin resonance, or in this case your electron proton resonance spectrum of methyl radical shows a negligible s character, uh, indicating thereby that its structure could be either planar or a very shallow pyramid. That means this does not show S character. If it does not show the S character, which one? The electron which is present on this free radical, that does not show S character. That means it is present in your pure p orbital. Mostly the planar structure is more stable as compared to your pyramidal structure. where the s character of the filled orbitals in various fluoromethyl radicals increases across the series. Like if we go from cs3 methyl free radical to your fluoromethyl free radical to difluoromethyl free radical to trifluoromethyl free radical, in that case the s character increases. That means here you most the carbon would be your sp3 hybridized, whereas in this case this carbon is your sp2 hybridized. The reason here is actually from going uh, and to your whenever we are attaching a more electronegative orbit electronegative elements, in that case the repulsive interaction between your singly occupied p orbital and the filled orbitals occupied by your lone pair of electrons on fluorine atoms is minimized by pyramidal geometry. Because in case of your trigonal planar structure, this electron which is present in your p orbital, so that is a kind of perpendicular to this is kind of perpendicular to these groups. Okay, so whenever we have this fluorine groups, fluorine has how many lone pair electrons? Three lone pair of electrons. So it faces repulsion from this because this is at 90 degree to each other. But whenever it is in a pyramidal structure, so that is away from it, and the bond angle here would be 109 degree 28 minutes. So there would be less repulsion. So when we put any groups which are having lone pair of electrons, then it prefers to stay in your sp3 hybrid orbital. So the actual structure is actually in between. So depending on your substituents, you can say that which would be its actual structure. The uh, pre-radical structure would be which one, whether it is planar or pyramidal. And this okay, so this generations, first of all, as you can just see, this is your planar free radical, in which one electron is in your p orbital, which can again uh, ele- uh, react with another chlorine to give you the R configuration, or it can give you your S configuration. Why it is so? This one is being proved that, like if we start with our any enantiomorically pure compound, then as it is giving a planar free radical intermediate, then the next incoming your free radical that can either attack on this side or it can go to this low, so generating the a racemic mixture R and S. That is as in our SN1 reaction, where we have a carbocation intermediate. So that intermediate is a planar structure. So the incoming nucleophile, in this case our incoming electrophile, can attack either of these lobes. You don't think that if we have put a dot here, that means the electron is only on this lobe, not on this lobe. Actually it is on the p orbital, so it is just go on up and down. Or you can just see, they as they are having pyramidal structure, they can immediately invert back to the other pyramidal structure, or it can give you the other enantiomer. Okay. uh, Next is the delocalization. Okay, for delocalization of this for its delocalizations, for its stability, like we know that for any intermediate, that should be stable, and this intermediate, whether there is a positively charged particle or negatively charged particle, they need to be stabilized, and this get stabilized by delocalization. So to get delocalized, this they have to be actually for delocalization, they should be of parallel geometry. So here we have a pi electron. So pi orbitals are being formed by your sidewise overlap of your p orbital. So if it is in a p, or if it is uh, for this delocalization to be possible, this free radical intermediate should be in a your p orbital, so that that would be parallel to this p orbital, so their delocalization is possible. For example, in this case also, our pi bonds are in benzene, the pi bonds are formed by the overlapping of all the six p orbitals of the six carbon atoms, and again this is sp2 hybridized. So the electron The radical or the electron is present in your p orbital, so that is in proper position for delocalization and for your stabilization. But sometimes when this unpaired electron is situated on a carbon at the bridgehead position in a bicyclic system. So for example, in this case, here actually planar configuration is cannot be attained by this carbon on this bridgehead position. So in that case, it will attain a sp3 hybridized structure. So which is actually the case that results of the APR spectra also says that okay, this is in a sp3 hybridized structure, or it is of a pyramidal geometry. So whenever it is necessary, that goes to your pyramidal geometry. For example, in this case, in this apocamphyl peroxide, when it on in presence of your light or heating, when you heat it, one carbon dioxide molecule is released, and that gives you apocamphyl radical, and which again undergoes other reactions, the chlorination or whatever reactions, to give you the product. So here actually in with free radical intermediate this is possible, rather with your carbocation intermediate it is not possible, because it would be difficult for a carbocation to be present in this position, because for a carbocation it has to be planar. Carbocation does not have a choice between planar or something, it has to be planar. So a bridgehead carbon can never be planar, but a radical free radical intermediate it can be planar sometimes, or it can be actually pyramidal. So this one is possible because of its pyramidal geometry, which cannot be attained in case of your carbocation intermediate. So next comes your stability of your free radicals. So for in case of your free radicals, the carbon is attached to three other groups or atoms. So from there it has 6 electrons, and again it has a one electron. So that means in total it has 7 electrons. So this is not octet. So this is actually electron deficient. We can say that free radicals are electron deficient, or these are electrophilic species. So that means they will be stabilized by the presence of an electron donating group. If we have an electron donating group, that will stabilize your free radical intermediate. So you just say tertiary is more stable as compared to secondary, as compared to primary, as compared to methyl, because in case of tertiary we have electron donating groups, that is your plus I groups, that is which donate electrons through inductive effect. So the more the number of plus I groups, which is more in case of your tertiary as compared to secondary. In case of secondary we have 2 plus I groups, here we have 3 plus I groups, here we have 2, here we have 1, here we do not have any plus I groups. So the more the number of plus I groups, more would be the stability. That's why tertiary tertiary free radical is more stable as compared to secondary, as compared to primary, and as compared to your methyl. Also this its stability, free radical stability, can be discussed by hyperconjugative effect, which we have discussed yesterday. So in this case also, the more the number of CH3 groups attached to your carbon bearing your free radical, the more would be the stability. So that is also the from hyperconjugative effect also you can say that tertiary free radical is more stable as compared to secondary, as compared to primary and methyl. That is because of your that is because of your hyperconjugation. So this bond should not be here, there should not be any bond here. Okay, so next effect is your resonance effect. Here you have, whenever you do this type of resonance, you have to do like this. So now uh, whenever there is a uh, carbon carbon double bond placed appropriately, or we can just say that that is present in conjugation with this free radical, they undergo delocalization to generate some other structures, or this free radical is delocalized to other carbons. So in that way that becomes more stable. So more the number of resonating structure, more would be the stability. For example, this is your allyl free radical, and this is your benzyl free radical. Benzyl free radical has more number of resonating structures as compared to your allyl. So benzyl free radical would be more stable as compared to your allyl free radical. So you have to do it like this. One electron is going there, one electron is going there. Both the electrons, the pi electrons, one electron is coming to this carbon carbon bond, and one electron from this radical is coming to this carbon carbon bond, generating a carbon carbon double bond here, and one electron is going to this carbon, generating a free radical. Again, this can undergo your delocalization, so that you would generate a radical here, then you can generate another radical in this carbon, so that will go on. So when you have three phenyl groups, as we have compared in case of your carbocation stability and carbanion stability, so whenever you have three more phenyl groups, the resonating structures increases and its stability increases. So if we just consider the order of stability of your different free radical intermediate, you just see benzyl is more stable as compared to allyl free radical as compared to tertiary. Although this is a tertiary carbon, and this is your primary carbon, but still this is more stable as compared to your tertiary, because here you have only your inductive effect, and here you have uh, resonance effect. Resonance is a stronger effect as compared to your inductive effect and hyperconjugative effect. So benzyl is a more stronger more stable free radical intermediate as compared to your vinyl, as alkyl and phenyl. So this one is less stable. The reason is you cannot just in case of your phenyl free radical or carbocation intermediate, whatever you have, this cannot be actually this is not stable. The reason is this cannot be delocalized onto your, so this cannot be delocalized onto, you just see this is not in appropriate position. This is not in appropriate position to get delocalized. The Because if we just see, in case for the delocalization to be possible, the electron should be on the p orbital, because these pi electrons are in p orbital, are in your p orbital. But in this case, your in this case, this p orbital is actually here. The pi bond is already in the pi bond is already formed by your p orbital, and this p orbital, if we just say, in this case it has to be your sp2 hybridized. Okay, for sp2 hybridized, the other p electron is 1p. Okay, in this case, it has to be in your sp3 hybridized state, because in that case, it would be difficult actually. So if it is in your sp2, one p orbital is used of, the p orbital is used of in your bond formation. So the electron, which is we are having the free radical that is present in your sp2 hybrid orbital. So sp2 and p orbital, there cannot be any kind of your delocalization or overlapping is possible. And again, this is not in conjugation, it is just present on the sp2 orbital. So here conjugation or delocalization is not possible. The thing is that actually the free radical in this case, if it is being formed, then it has to be present on your sp2 hybrid orbital. So that is not necessarily actually being formed, that is not very stable. Next is your steric effects. So if we just sometimes the steric effects plays a very important role in the formation of your free radical intermediate. So if you just see, this is our isobutane. So this one is favored onto this your butyl free radical. The reason is that by the formation of a by just removal of this hydrogen, now that forms a tertiary butyl free radical. So now in this case, when it was your this is your isobutane, here the bond angle was 109 degree, and they were having steric repulsion. But by converting, or by just the expulsion of your hydrogen, that which forms a free radical, which generates a free radical, by the formation of that free radical, now this is your sp2 hybridized, and the bond angle changes to 120 degree. That attains, this is a tetrahedral, and this is a your trigonal. So the bond angle increases. So in that case, your steric crowding is decreased, or there would be less repulsion between your ch3 groups. Similarly, in case of your 2,6-ditertiary butyl phenoxy radical, which exists in solution and in the solid state. Mm, Actually, some free radicals exist in the uh, um, we can just isolate it. This one, for example, this free radical, you can isolate it. The reason is like it does not form a dimer, but if we have RO dot, then it immediately dimerizes to give you ROOR. But here it does not get dimerized because of the actually its steric chemistry, steric effect. Here you have three CH3 groups, so it just does not uh, allow the other radical to approach this one. So that's why this free radical is very stable. You can just isolate this free radical. Next is how you detect your free radicals. So, like in your reaction mixture, how you know that we are having free radical as an intermediate. So, you can do add one radical inhibitor or radical initiator to your reaction mixture. If your reaction rate of reaction increases, or if your rate of reaction decreases, then you can just make sure that okay, the reaction must be going through a radical intermediate. Or if that does not, if it does not change, the rate of the reaction does not change, or uh, there is no effect. Just a minute, I have to take this call. Just 1 minute. Okay, sorry, but I had to take that call. Okay, so if your reaction, like if you have a doubt that okay, my reaction is going through free radical intermediate, then you add another radical inhibitor or radical initiate into your reaction mixture. It three things can happen: either your rate of reaction will increase, or your rate of reaction will decrease, or your it won't be affected. If it is not affected, then in that case you would say that okay, the reaction does not go through your free radical intermediate. If it is then if it is and the rate of reaction is increased or decreased, in that case you can say that okay, our reaction is going through a free radical intermediate. So radical intermediates, inhibitors, for example, suppose in case of this one, we have in our reaction mixture we are generating one radical. So if we add one inhibitor, for example hydroquinone, that will immediately inhibit the reaction by just taking out this free radical. That even it would take out the electron, or it would give out another H dot, forming your alkane or whatever be the product. And this hydroquinone radical, this is being formed because that is your resonance stabilized. So from that you can just say that okay, our reaction is going through a free radical intermediate. Even this free radical intermediate can be trapped, and you can analyze the product. So this trapping of free radical is used in which actually we cannot detect our free radical which is very unstable, highly reactive. Then in that case you can do any method. First of all, in this case there is a cross coupling trap which gives a cross coupled stable product, and you can just like do the analysis. From that you can just know that okay, I have used this one and it have attacked this one though. So that might be like, here we can just say that our free radical is trapped. For example, this R dot and this one, that is giving you this radical adduct. So this radical adduct now can be identified by your ESR, electron spin resonance spectroscopy. So that signifies that free radical intermediate is your formed, because this free radical intermediate cannot be easily detected in your ESR spectroscopy. Similarly, you can trap other radicals also by different trapping techniques you can use. So, what is this electron spin resonance spectroscopy, and how it is being used? Actually, electron spin resonance, if you have in your BSc, I think you have learned about NMR, nuclear magnetic resonance spectroscopy, where you mostly study the nucleus. That is your PMR or CMR, proton magnetic resonance spectroscopy. It is similar to that one. Here we detect the electrons. So, electron spin resonance spectroscopy is a technique used to study your materials containing unpaired electron. It works by exposing a sample to a microwave radiation within a magnetic field, so causing transitions between the energy levels of the unpaired electron. Suppose we have, in case of your, whenever you have a free radical, now this free radical can have two states. In the presence of a magnetic field, it would have two states. Two energy levels. One would be aligned to the magnetic field, and the other one would be your opposed to your magnetic field. So at the room temperature it would be aligned to your magnetic field. So when you give appropriate energy, that is in the microwave radiation, when that is exposed to your microwave radiation, so that one undergoes spin flip, that will go from your ground state to your higher energy state, that gives you a peak. So this transition from stable state to your higher level state gives you a line in the spectrum. So this at high resolution, this single line is split into several lines due to the coupling of unpaired electrons with the protons of the atom, which carries this odd electron. If you just see, okay, we have one electron, then we would get a single line. We are getting many lines, and this splitting of lines actually gives the idea about its environment. For example, in case of your CH3, that is your methyl free radical, that gives actually 4 peaks. So that is equal to actually n plus 1. N is your number of protons present plus 1. So in case of your methyl free radical, you get 4 peaks, and in case of your cycloheptatrinyl radical, where you have six hydrogens, one, two, three, four, five, six hydrogens. So the in total you would get seven, one, two, three, six, seven, and one, two, three, eight. So it should have seven protons. So yeah, because here you have another proton. So seven protons. That's why you are getting eight peaks here. So what is the reactions, how these free radical reactions, free radical intermediates react, the mechanism? Actually, this mechanism of free radical reactions mostly contains your initiation step, propagation step, and last one is your termination. So this is a kind of chain reaction where every first step is your initiation. In initiation, first is the generation of your free radical, and then it attacks in your propagation step, then that attacks your whichever substrate you have, and it generates a free radical again, and this free radical will again attack another molecule, may attack another molecule, or it can attack your chlorine and dot to get another chlorine dot. So this step goes on, this propagation step goes on, or this goes on, like again this chlorine dot will attack another substrate molecule to generate the AB. So this A and B steps continues uh, until and unless you're in the reaction condition you have more of CH3 dot, or you are adding some inhibitor from outside, otherwise this will go on. So that is a kind of your chain reaction, and in every propagation step you would see that every step generates a free radical. So in the finally, when there is concentration of, or whenever a methyl free radical and chlorine free radical that comes in contact with each other, then that terminates there, the reaction stops. Or two methyl free radicals gives you ethane, or two chlorine free radicals gives chlorine. So there is one reaction, that is your substitution radical nucleophilic unimolecular reaction. That is a nucleophilic substitution reaction in your aromatic compounds, that also goes through these three steps: initiation, propagation, and your termination. So first of all, for example, if we start with our halobenzene, so first one electron will be lost from this one to generate a free radical, and from that X minus is expelled, or uh, actually departed to generate your R dot, and now this can another nucleophile can be attacked here to give you your product, or in presence of your RS that can go back to this would be your byproduct benzene. So this is the same radical nucleophilic aromatic substitution reaction. For example, your Sandmeyer's reaction from benzene to get your iodobenzene, where actually direct iodination is not possible. You can go through this pathway. So from your diazonium chloride, when you treat it with the iodide, so first that generates your uh, diazonium radical, where your diazonium from the diazonium radical, nitrogen is expelled or departed. The leaving group is departed to generate your uh, phenyl radical, which again takes off your iodide, and that reacts with another molecule of your diazonium to generate your iodobenzene, and to generate your diazonium radical. So that cyclic process goes on, and in each step, uh, one diazonium one diazonium salt is added and one iodobenzene product is being formed. So sometimes when this reaction is being carried out in a solvent cage, where there is no chance of the other molecule, like in this case we have the chance of your diazonium salt to come in contact with this iodide iodobenzene radical. So if we have a solvent case where there is no chance of the actually chance of the approach of another molecule to undergo this chain reaction, so in that case it just stops at one chain. Okay, it does not undergo chain reaction. That is known as your case effect. Next is some other free radical reactions. So first important reaction is your substitution reactions, where your hydrogen of mostly in case of your alkanes we can do direct halogenation. And so where your hydrogen is being substituted by one free radical, halogen free radical. For example, in case of your chlorination, if you treat it with methane, that gives you uh, chloromethane. Similarly, it can give you with your propane, that can give you chloropropane, one chloropropane or two chloropropane. So there you can get many number of products in case of your chlorination, because chlorination is highly actually exothermic. If you just see the del H value is highly negative, so this is not very selective. You get a many products because chlorination is highly reactive. This is an exothermic product. But in case of your bromination, as you can see, this one is being endothermic. The reaction is very selective. So for example, when you have a isobutane, the tertiary butyl bromide is the major product as compared to your primary bromide, because this hydrogen is being replaced more this hydrogen is being substituted by your bromine free radical as compared to this one, because in the this actually it first forms a free radical intermediate. So we know that tertiary free radical is more stable as compared to secondary as compared to primary. So as bromine is very less reactive, so this one is selective. So you, but here it is not selective. You are going to, in case of chlorination, you are going to get a mixture of products. In case of your bromination, there is one problem is that bromine water. Actually, we use bromine water in case of your bromination, and it is a very pungent smell and very difficult to handle. So, in presence of bromination, in presence of your in actually for its substituent, we can substitute bromine in with n-bromosuccinimide, which is a reagent which gives in situ, which generates bromine in situ, means in the reaction mixture itself. So this is your n-bromosuccinimide in presence of HBr, that gives you succinimide plus bromine, and this bromine will again undergo reaction to give you your product. And this NBS, this reagent n-bromosuccinimide, is a very good reagent for the allylic bromination. Next, what about our iodination and fluorination? Actually, if you just see, in case of your iodination, all the del H values are positive. That means this is highly endothermic, so it is very difficult to carry out this reaction. And another reason is that this reaction is actually reversible because it forms, suppose I just go CH4 plus I2, that gives Hi plus CH3I. This reaction is actually reversible. The reason is that Hi, this is a very good actually reducing agent. So whenever it is formed, it again reduces CH3I and again goes back to CH4 because it itself gets oxidized to your iodine. So that's why this reaction is reversible, and this actually yield is very low. And in case of fluorination, as you can see, this del H value is very negative. So this is highly exothermic and it is difficult to actually control this reaction. The fluorination is highly explosive. So among fluorination, bromination, and iodination, iodination is very slow, fluorination is highly reactive, so you cannot control it, and chlorination is okay, but that is not quite selective. So bromination is selective and the good. Next is addition reactions. Halogens can be added across the carbon-carbon double bond, and this is a very good method for the actually conversion of cis to trans. The reason is, first of all, when our bromine radical, okay, from bromine we generate bromine molecule, we generate bromine radical. So now this will attack here to generate a carbon free radical here, and now this can undergo rotation, and whenever this bromine is like this, now we have a carbon carbon single bond, so now it can undergo rotation. So when it is not rotated, then it is going to give you the cis product, but when it is rotated, this carbon carbon single bond, so now this carbon and this chlorine will come to the down, and in that case that is going to give you the trans product. So this is a very good method for the conversion of your uh, trans sorry cis to trans, because trans is more stable as compared to your cis product. So in that would be more in your equilibrium, that will predominate. Next is addition of your halogen acids. So this is undergoes in a anti-Markovnikov pathway. As you know that in case of your HBr addition, and when we do not use any peroxide, in that case your it is a electrophilic addition reaction, where first your H plus is added, giving the more stable carbocation, then your bromide will is going to attack that position where you have your carbocation intermediate. But in this case, in presence of an in presence of an initiator, or in presence of an peroxide, this generates a bromine free radical. So this bromine radical, whenever it undergoes addition here, it can give a secondary free radical, or the bromine can go to carbon number 2 or 1. If it goes to carbon number 1, then that generates your secondary free radical, or if it goes to carbon number 2, then that generates a CH3 CH BrCH2 dot. So this one is this primary free radical. So that one won't be formed. This secondary free radical will be formed. So now this secondary free radical again takes up your hydrogen radical to give you your 1-bromopropane. So in the addition of only HBr, you get 2-bromopropane as the major product, but in presence of one peroxide, uh, mostly your organic peroxide, not hydrogen peroxide, organic peroxide, that gives you 1-bromopropane. Or in the sense, we can say that this effect is known as your peroxide effect or your Kars effect. So that gives you anti-Markovnikov's product, but the mechanism tells the actual result, because here the more stable free radical predominates, and here more stable carbocation intermediate predominates. And instead of HBr, this peroxide effect is only applicable in case of your addition of HBr. In case of your addition reaction of HCl and HI, this normally does not take place. The reason is that in case of your uh, uh, HI, you just see this is highly endothermic. This one and this one, both the steps are highly Your first step is highly your endothermic, although the second step is exothermic, but still the first step does not have that much energy to take out your carry out your reaction. And in case of your chlorination, the first step is uh, highly exothermic. So in that case, it does not just simply stays here, it undergoes polymerization to give you a polymer. So that uh, low polymer weight, okay, low molecular weight polymers, but still your chlorination does not just undergo your substitution, rather it goes polymerization. So these low weight polymers are known as your telemers. Next, these free radicals can also undergo auto-oxidation to give hydroperoxides. Uh, in this case, as you just see, that can generate this free radical in presence of oxygen that gives your hydrogen peroxide. Okay. So, for example, in this anthracene molecule, so in presence of sunlight, this can give this free diradical intermediate. Okay, so now this diradical in presence of oxygen, oxygen is itself a diradical in nature. We know that oxygen, the molecular orbital structure of oxygen, its two electrons are present in your pi to px and pi to py orbital. And they are actually in radical form, means singly occupied. Here you have one electron in pi to px orbital and pi star, sorry, these are pi star orbitals, and in your pi to pi there is one electron. So these are diradical in nature. So they react with this diradical to form this compound. And similarly you can see other reactions also. So oxidation with lead tetraacetate. When lead tetraacetate, actually first this is a very good oxidizing agent. So it undergoes dissociation to form lead diacetate plus two acid oxy radical. This two acid oxy radical takes out proton radicals from this cis diol to form this to form this diradical, which again undergoes dissociation to form ketones or aldehydes. So depending on these R groups, it can be ketones or aldehydes. So this is actually seen that cis diols are cleaved considerably faster than the trans isomers. So that shows that this is the reaction mechanism. Next is it can undergo some rearrangement reaction. For example, in this free radical intermediate, so here we have two phenyl groups and one methyl group. So among this one phenyl group that undergoes migration or rearranges, it goes shift to this carbon to generate this another free radical which is more stable, because that would give you a free radical like this. Okay, so that would give you one carbon dioxide is being removed, that first gives you a free radical like this. So this free radical is being stabilized by the shifting of your phenyl group. So always as we have discussed yesterday, migratory aptitude of phenyl is more as compared to other groups. Next is your radical ions. Sometimes in your reaction mixture, you get some radical as well as your ions. For example, when you, from any other source, you just give one electron to benzene. So in that case, here you would have a negatively charged particle as well as one, uh, as well as well as you would have a radical. So which one is being actually stabilized by resonance, you can just see. So or one electron can be removed to give you a benzene radical cation. So you can have a radical anion or you can have a radical cation. For example, in case of your hydroquinone, that when you remove one electron from in presence of your OH minus, uh, electron is removed, so it just gives you O minus, and in this case your O dot. So this radical anion is being resonance stabilized, and in presence when you give H plus, in that case that again gives you hydroquinone and quinone. The similarly you can have different radical cations also. For example, when this your tertiary amine, okay, dimethyl NN dimethyl orthopara, NN dimethyl benzene. So when one electron is removed from it, it can be taken out from this lone pair of electron. That gives you a radical cation, which is being resonance stabilized. So these are all about your free radical intermediate. Next, we would come to your carbene as intermediate. Carbenes are the intermediates in which your carbon is attached to two groups and you have a lone pair of electrons. So in total, carbon has actually four electrons, and among these four electrons, two are taken part in bonding and two electrons are remaining. So you have three electron pairs, two bond pair plus one lone pair. So how you generate these carbenes? Okay, and so these are the different carbenes. This is methylene dichlorocarbene, diphenyl carbene, cyclohexylidene. So these are different carbenes. And how these carbenes are generated? Actually by your photolysis method or thermolytic methods of your diazomethanes. So when diazomethane is treated with in your light or heated, then that gives you methylene, and nitrogen gas is removed. And even ketenes also, in presence of light or thermal condition, that gives methylene. Even this can be generated from your haloalkanes, like chloroform, in presence of a very strong base, that gives you dichlorocarbene. So in this case it has to be very strong base. From methylene iodine also, iodide in presence of zinc, uh, first it would give you iodomethyl zinc iodide, which again uh, mm, undergoes disproportionation reaction to give you methylene and zinc iodide. Actually, this organic compound CH2Z and I2 is known as a mast carbene, and this is actually industrially available. So means it is in your reaction mixture that gives you methylene or a carbene. So that's why this is known as your carbenoid or carbene like. Then there is another methods like thermal decomposition of your trihaloacetates. This is your trichloroacetate, sodium trichloroacetate. So first that gives you carbon dioxide. First it undergoes decarboxylation to give you carbon dioxide and sodium trichloromethane, and again that undergoes removal of your sodium chloride to give you dichloromethane. So there are different methods even from epoxides also, like from alkenes, you treat it with por acid, that gives you one epoxide, and this epoxide undergoes actually bond cleavage to give you your carbene intermediate. Okay, yeah, from there are other methods also from diazirines, from tetrazoles. Tetrazole means whenever you have a five-member ring with four nitrogens present here. So in the first step, nitrogen is removed, nitrogen gas is removed, and then it can undergo like different conditions, like first nitrogen gas would be removed, that would take out this proton, then it would go a number of steps to give you a carbene. So from ylides also, ylides are actually whenever you have a like positive and negative charged ion, which is actually bonded together a sigma bond, that is your ylides. So from ylides also we get your carbene intermediates. The next is the most important part, that is your structure and stability of carbons. So as I told you, carbon, in this case carbon is having four electrons and two are being bonded, and you have two electrons. Okay, so these two electrons can either be present in one orbital, or it can be like if it is a three electron pair, then it can be sp2 hybridized. So if it is sp2 hybridized, then in that case two sp2 hybrid orbitals are used of in bonding, and the lone pair of electron is present in your sp2 hybrid orbital, and you have a empty p orbital. Or you can just put both the electrons in two different p orbitals. So in that case that would have a sp hybridization. So in case of your whenever it has a sp2 hybrid orbitals, both the electrons are present in your sp2 hybrid orbital, and in this case both the electrons are present in your each orbital, one electron in each orbital. That is according to your Hund's rule. So in this case, this carbon is known as your singlet carbon, and this carbon is known as your triplet carbon. Actually, that depends on your spin multiplicity. As here we have both the electrons in the same orbital, so their total spin is plus half minus half, that is equal to 0. So the spin multiplicity, that is 2s plus 1, that is equal to 1, because s is here 0. But in this case, this is known as your triplet carbon, because one is in your both are in all different orbitals, so they both have plus half spin. So in total they have s is equal to 1, so 2s plus 1 is equal to 3. So here the spin multiplicity is 3, that's why this is your triplet carbon. And in this case the spin multiplicity is 1, that's why this is your singlet carbon. So singlet carbon is less stable as compared to your triplet carbon, because in this case you would have electron electron repulsion, because both the electrons are present in the same orbital, and in this case there would be less electronic repulsion. So this stability of this, again, as I have told, in case of a free radical intermediate, the stability of singlet carbon and triplet carbon depend on the nature of your R groups. So if you have some R groups which are having heteroatoms such as chlorine, fluorine, bromine, iodine, in that case they stabilize your singlet carbon by donating their electron, because they have lone pair of electron, they can donate electron to this orbital. And again the orbital, the lone pair of electron on the orbital on this carbon can again go to the available vacant orbital in case of your fluorine or bromine or iodine. So that it is a kind of back bonding. Here you have bonding as well as back bonding, so that stabilizes your singlet carbon. So next comes your reactions of carbon. I think we can just take a break here for 5 minutes. Should we take a break for 5 minutes?
Yes, ma'am.
Okay. Yeah. Okay, till now, everything is clear. If you have any doubt till now, you can just ask me. Are you all there, or you are not back from break?
No, no, ma'am. Yes, ma'am.
Okay, okay. Okay then. Now carbons are of two types. One is your singlet carbon and one is your doublet carbon. So singlet carbons are actually that depends on your substitutions. But in the ground state, most of the carbons are present in your triplet state. So carbons reactions can be of any type. It can be addition, insertion, or rearrangement. And mostly your singlet carbons behave like an electrophilic species, uh, as in case of your carbocation intermediate, carbon monoxide, and isocyanides. And your triplet carbon, they mostly behave like a radical because that is a diradical, we can say. And first reaction is your cycloaddition reactions of your carbons. So once the carbon is generated, for example, from your bromophore, in presence of your tertiary butoxide, that generates your dibromocarbon. And this dibromocarbon, that is in the singlet state, that undergoes cycloaddition reaction to form a cyclopropane. So your trans 2-butene give it is a stereospecific reaction. Like trans 2-butene will give you trans dimethyl dibromocyclopropane, and your cis 2-butene would give you cis dimethyl dibromocyclopropane. So your cis would give you cis. But if this reaction is carried out in presence of an inert gas, in that case the singlet methylene generated initially gets converted to the triplet state. So in this singlet methylene will now be your triplet methylene. So that will add up. In this case, actually both the it undergoes cycloaddition like this. So that would be as this is a singlet carbon, both the electrons are present in one orbital. So that would attack this carbon, and this pi bond electron will attack this carbon. So that would take part from the same side. So that would undergo your cycloaddition reaction in case of your singlet carbon. But in case of your triplet carbon, now in case of your triplet carbon, one electron, so this carbon would be bonded to this carbon, and it would generate your this type of intermediate. Now this carbon carbon single bond uh, can either undergo rotation and then spin inversion, because first of all this would be parallel spin like here, so there won't be any bonding. So now this intermediate has two chances, like it can undergo first spin inversion and then bonding, spin inversion and bonding to form your cis product. And or it can just, now we have a single bond here, it can just rotate in this fashion and undergo spin inversion to give your trans product. This would be more stable as compared to your cis product. So your singlet carbon is stereospecific in nature, but your triplet carbon is not stereospecific. Okay, in case of the addition of your singlet carbon, or we can just say the syn addition of a carbon to cyclic alkene gives a bicyclic product. For example, when cyclohexane is treated with this carbon, that gives you a bicyclic product. And sometimes this cycloaddition reaction can be followed by a ring opening process. For example, this pyrrole, when treated with your uh, alkali, that generates your nitrogen intermediate, which in presence of your dichlorocarbon, that gives you this addition reaction. And now this addition reaction, that is your fused ring cyclic or bicyclic product, undergoes ring expansion to give you here this pyridine derivative. Similarly, this six-membered ring undergoes your first it undergoes addition, then undergoes your ring opening process to give you a seven-membered ring. Next is your insertion reaction. Insertion means this carbon is being inserted between a bond, between the two atoms of a bond. For example, in this carbon hydrogen bond, our uh, this methylene carbon is being inserted, so the final product is your ethane. For in this propane, so now you have two types of in case of your propane, you have two types of carbon hydrogen bond. One is the carbon hydrogen bond here, and one is your carbon hydrogen bond here. So that can either add to your carbon hydrogen bond on the terminal carbon or onto the actually your middle carbon. So that generates two different product ratio. So this insertion reaction with higher alkanes lead to a complex mixture of your isomeric products. Like here we get N-butane and your isopropane. So two isomers are obtained, and one is bigger, larger as compared to other. One would be your major product, one would be your minor product. So it is supposed that the back lobe of the carbon hydrogen bond is involved in insertion reaction. Like here we have the bond. So now on the insertion, this carbon will be inserted to the back lobe of this, like you have a back lobe here, so it will be added to the back lobe of this bond. So that gives you an inversion in configuration. And as it is adding the back lobe, so it is better, it attacks mostly on the terminal carbon as compared to your middle carbons. And for example, as it is, and again as it is being added onto the backside, so there would be an inversion in configuration. For example, uh, in this insertion reaction to this carbon hydrogen bond, just you see here, in this case the carbon hydrogen bond or this hydrogen is off the plane. So when this CH2 group is being added, now this OAC is acetate group is up the plane and CH3 is going down the plane. Because CH2 group is added onto the backside of this carbon hydrogen bond, so now OAC would go up and CH3 would come down. So there are other insertion reactions in which uh, in the previous reaction the carbon has been inserted onto your carbon hydrogen bond, and in this reaction your carbon is being inserted onto your oxygen hydrogen bond. So that gives you, like in this case, that gives you an ether, and in case of reaction with your acid, that gives you an ester. So these are very good methods of synthesis of ethers and esters. And unlike your carbon hydrogen bond, we know that oxygen hydrogen bond is a polar bond because oxygen is more electronegative as compared to your carbon. And the reaction is supposed to be proceeded through, like first of all, this carbon intermediate would take out proton to generate your carboxylate ion. Now this carboxylate, as this is a polar molecule, so now this carboxylate ion will react with your this intermediate diazonium methane to generate your ester plus nitrogen. So this is your insertion reactions of carbons. Next, some rearrangement reactions and other reactions of your carbons. So first of all, it has a wolf. It can undergo wolf rearrangement. So this diazonium uh, carbon. So of no, so this diazonium compound, and that is your diazoacetophenone. So this diazoacetophenone, which is actually resonance stabilized, which is being resonance stabilized in these three structures in presence of silver oxide, that generates this carbon intermediate. So this carbon intermediate undergoes rearrangement to give you this phenyl ketene. It will go off, then it will come out. This will go to your this carbon. That is your rearrangement reaction. Let me do it more properly. So we have a lone pair of electron on here. So that will go to this carbon single bond. Now that will become a carbon double bond. So this will go up, and when it come down, this electron. So now this C6H5 group will migrate to this carbon. So you would have C6H5 CH carbon double bond, uh, carbon oxygen double bond. So that gives you a phenyl ketene intermediate. So now this phenyl ketene intermediate uh, has many fates depending on your reaction condition. So if you react it with water, then that gives you phenyl acetic acid because it gets hydrolyzed here. OH group would attack here, so that gives you phenyl acetic acid HOH. HOH. Or it can react with your alcohol to give you ester. It can react with amine, and it can react with your ammonia to give you amide. Even another reaction which relate to your carbons are your ring contraction reactions. For example, your diazoketone in presence of your light and methanol. So that first generates your carbon intermediate and nitrogen is removed. Nitrogen gas is removed. Now this carbon intermediate will undergo rearrangement to give you your that undergo ring contraction. Actually, by rearrangement, now this bond breaks. So this lone pair of electron undergoes your, it goes to this carbon carbon double bond, a carbon carbon single bond to form your carbon carbon double bond. So now this pi bond, carbon oxygen pi electron will go to oxygen and again it will come back. So in that case, this bond will now migrate to this carbon. So this carbon, like, it is no longer attached to this carbon, this is to this carbon. So now you have a ring contraction. So now if you treat it with methanol, that gives you, and this double bond won't be here, okay, that gives you a ester. Next is Riemann reaction, which gives the that is the most common reaction for the preparation of your salicylaldehyde, which is a very important chemical. So Riemann reaction involves first the generation of your dichlorocarbon from your chloroform, that is in presence of your potassium hydroxide. So now this undergoes, actually dichlorocarbon is an electrophile. We know that because it is electron deficient. This carbon is having in total 6 electrons. So it undergoes electrophilic substitution reaction. So in case of phenol, we know that in presence of OH minus, that would giving you phenoxide ion, and this phenoxide ion or OH group is ortho para directing group in case of your electrophilic substitution reaction. So that will attack your electrophile at ortho position and para position. There is equal chance of formation of your ortho product and para product, but as salicylaldehyde, the ortho product is your most important product which is being used in your industry. So this mechanism is given here. So first it undergoes electrophilic substitution and then series of substitution and elimination reaction to give you the final product, that is your salicylaldehyde. This is also used in the carbylamine reaction, which is a very good reaction for the distinction between primary, secondary, and tertiary amines. Actually, in case of your carbylamine reaction, only primary amines respond to this reaction. Secondary and tertiary amines do not respond to this reaction. So this you can distinguish your primary amines from other type of amines. So what is the mechanism of this reaction is, here also first is the generation of your dichlorocarbon in presence of a base from your chloroform, and this dichlorocarbon, again this is this is an electrophile. So in presence of your nucleophile attacks your this dichlorocarbon, then it undergoes many elimination reactions to generate your isocyanate. So this isocyanate is having a very bad smell or odor, foul odor or smell. So from that you can know that you are having a primary amine. If it is not, does not give any this bad smell, then you know that the amine that is provided to you is not a primary amine, rather it may be a secondary and tertiary amine. Next is some reactions. There are some industrial preparation of your orthoformate ester, in which your dichlorocarbon is treated with ethanol. Here you have your insertion reaction that is being inserted onto your oxygen hydrogen bond, and when you treat it with another two uh, ethoxides, so that undergoes these two chlorines will undergo actually nucleophilic substitution reaction to give you orthoformate ester. Okay, then there is another class of reaction that is your Wittig reaction. Your dichloromethane, when you react it with uh, triphenyl phosphine, that gives you one ylide, phosphorus ylide. So this lone pair of electron reacts here. So now you have a phosphorus already given its lone pair of electrons, so that acquires a positive charge, and you have a bond between phosphorus and chlorine, and you already have a lone pair of electrons. So now that will acquire a negative charge on carbon. So this is a kind of halide. So this halide, when reacts within your carbonyl compound, so that this acts as a, this is your nucleophilic center, this is your electrophilic center, so that react with this one to generate this compound, which cyclizes to give you this product, and then it undergoes concerted manner, in a concerted manner the bonds are being broken to give you one alkene and some phosphorus oxide. So this is the reaction in case of your Wittig reaction. That is the reaction from where you go from your ketone to one alkene. And depending on, like, you can increase your number of carbon atoms in this case, and also depending on your type of what is your requirement, you have to choose your carbon here. Next intermediate is your nitrines. Nitrines is mostly similar as to your carbons, and in case of nitrines, as we know that in case of your ammonia, amine or nitrogen is having a lone pair of electron, and in this case of nitrine, we have already one lone pair of electron and another lone pair of electron is also there. And nitrogen is bonded to only one atom. So how your nitrines are generated, then we will discuss about its stability and structure and its reactions. Okay, so nitrines are generated from your azides, either photolytically or in thermal process. So when azides actually in thermal process or in presence of light, that gives you nitrine and nitrogen as your living group. So there are different type of azides which gives you your nitrine intermediate. Even from phosgene, when phosgene, from phosgene also you get azidoformate, which again undergo your decomposition to give you ethoxycarbonyl nitrine. So there are many methods in which you can generate your nitrines from different azide, from different azides. For example, from this phenyl azide, you can get your phenyl nitrine, and this nitrine can undergo actually cyclization reaction. And again, like in case of your carbon, it can undergo cyclization and then it can undergo ring expansion to give you a larger membered ring. So similarly, from oxidation reduction reactions also, you can generate your nitrines from cyanamide in presence of your phenyl diacetoxyiodide or lead tetraacetate, you can generate your nitrines. Even from isocyanates also, isocyanates in presence of actually light uh, he- or if you heat it, you generate your nitrine and carbon monoxide. And there are other methods also, from oxaridins, from sulfonylamines. In every case you have a, you do it in photolytically or in thermal process. So from oxaridins, oxaridins are actually a three membered ring where you have a nitrogen, oxygen and carbon in your ring, so that undergoes decomposition to generate say carbonyl compound and one nitrine. Similarly, from N-benzene sulfonoxycarbamates also you can get your carbon nitrines. Next comes the structure and stability of nitrines. So here the nitrines, as in case of your carbons, this can be singlet nitrine or it can be triplet nitrine. So one lone pair of electron, we do not have to consider this lone pair of electron because that will always be present in your hybrid orbital. This lone pair of electron of nitrogen, only we will consider this pair of electrons. So either these two electrons will remain in one orbital, then in that case it will be singlet nitrogen. And when these two electrons are remain in two uh, p orbitals, one in each p orbital, then we can have your triplet nitrogen. So in that case, either your singlet nitrogen, here it can be sp2 hybridized, or here it can be sp hybrid orbital. So when it is sp2 hybrid orbital, this lone pair of electron is in your sp2 hybrid orbital, this is also sp2, this is bonded through your sp orbital, and you have a empty p orbital. And in case of a triplet nitrogen, the nitrogen is hybridized, and one bond is formed through this sp hybrid orbital, and this lone pair of electron is present in sp, and you have two pure p orbital and one electron are present in each p orbital. So, experimental evidence shows that nitrins are initially formed in singlet state, then they undergo intersystem crossing to give you triplet nitrogen, because triplet nitrins are more stable as compared to your singlet nitrins. So, as we have discussed in case of your carbon, singlet species arch to multiple bonds in a stereospecific manner, whereas in the case of your triplet species, which behaves more like a diradical, the addition would be non-stereospecific. We'll discuss this. As in case of your carbon, this is almost similar. Further, the singlet nitrogen inserts into carbon-hydrogen bonds, while the triplet species abstracts your hydrogen. So the nitrogen intermediates are highly reactive, therefore it is difficult to isolate. These are stabilized when reaction with monoxide and carbon monoxide and alkanes. Okay, you can trap your nitrogens, uh, and it can be stabilized. Then comes your reactions of nitrogen. So it can either undergo isomerization, hydrogen abstraction, coupling, or dimerization, uh, or many other reactions. So in case of your isomerization, like it would take out one proton from here, and from nitrogen it would give you a imide. And in case of your hydrogen abstraction, it can abstract hydrogen from any other molecule to form your amine. And okay, it can also undergo some rearrangement to give you I- cyanides or nitriles. Okay, first it undergoes means takes out one proton from this carbon to generate your imine, and this is tautomeric with your nitriles. It can undergo coupling or dimerization, like two nitrogen intermediate dimerize to give you diimides. Okay, or it can abstract hydrogen from any compound, like from any molecule to generate a free radical. For example, this alkyl azidoformate, first generation of this nitrogen, and this nitrogen, first singlet nitrogen, then your uh, triplet nitrogen, then it would abstract proton from another molecule to give you alkyl carbamate. And here also, uh, from starting from your benzoyl azide, first you generate your this nitrogen intermediate singlet, then it goes to your triplet nitrogen, and then abstract of proton from any other molecule to form your benzamide. So insertion reactions. In insertion reaction, as we know that the nitrogen is being inserted between a bond, between the two atoms of a bond. So its order of reactivity is that it easily inserts into a tertiary carbon hydrogen bond as compared to secondary, as compared to your primary. So for example, in this case, uh, this nitrogen would be inserted between this carbon hydrogen bond, forming this is our product. For example, when we have two different types of your hydrogens, in this case we have a secondary hydrogen carbon hydrogen bond and a primary carbon hydrogen bond. So it would insert to your this carbon hydrogen bond, which is your secondary carbon hydrogen bond, forming the major product, and this one would be your minor product, where the nitrogen is inserted between your carbon hydrogen bond, which is your primary carbon hydrogen bond. Sometimes your nitrogen insertion in a carbon hydrogen bond leads to ring closure. For example, in this reaction, first it would generate a carbon here, and okay, it would generate a carbon here from this azide, and now it would insert this carbon hydrogen bond in this carbon hydrogen bond to form this compound. So that mm, gives another ring, or it gives you a fused bicyclic product. Next is your thermolysis of cyanogen hydrazine. So this is your cyanogen hydrazine, cyanogen azide that first forms this nitrine. Okay, so this nitrine, when you treat it with cis, that gives you, this one is the major product, and trans, in that case, that gives you a major product. So in case of your singlet nitrine, that actually inserts stereospecifically, but in case of your triplet nitrogen, that would undergo, actually, like in case of your carbon intermediate, that would undergo spin inversion or carbon carbon bond rotation to give you a different product. So that is not so stereospecific. And in this case, your, this is a kind of your intramolecular insertion, because here it generates the nitrogen here, and this one would be being inserted here. So that is a kind of your intramolecular insertion reaction. Next is your 1,3-dipolar cycloaddition reaction. So cycloaddition, in case of your cycloaddition reaction, that gives you a cyclic product first of all. So when ethene reacts with your imine, that gives you aziridine. So it undergoes, actually, and we can just say that reacts here, and this comes, the bonds comes here. So it cannot, this one is the case of your 1,2 cycloaddition. And what is your 1,3 dipolar cycloaddition? First of all, we should know what are your 1,3 dipolar molecules. For example, ozone is a 1,3 dipolar, because as you can see, 1 2 3. So this is a 1,3 dipolar molecule, where you have a 3 atom and 4 pi system. Ozone, azides, diazo compounds, acyl nitrins, these are your 1,3 diazo compounds. So when this is treated with, these nitrins are treated with any of this 3 diazo compounds, or any 1,3 dipolar cycloaddition, it undergoes 1,3 dipolar cycloaddition reaction to form a cyclic compound. So the products of such reactions are actually your 5-membered rings. For example, this one is our nitrine intermediate. When this is treated with your phenyl or benzene cyanide, that gives you 1,3,4 oxadiol. So this is a kind of your 1 2 3. This is a dipolar compound. So that undergoes cyclization reaction. Next, alkenes can be added to your nitrines. Singlet nitrine would give you a stereospecific product, and if singlet nitrine under specific reaction condition, it would undergo intersystem crossing to give you your triplet nitrine, which would give you a non-stereospecific product. So as in case your carbon intermediate, whenever we have singlet nitrine, for example, cis-butene would give you cis-aziridine, and trans-butene would give you trans-aziridine. But if you have a triplet nitrine, then that will undergo a spin inversion, and cis would give cis as well as your trans-aziridine, in which you would have a carbon-carbon bond rotation. You can just check it in case of your carbon, it is almost similar. Next is rearrangement reactions of nitrines. So nitrines undergo 1,2 alkyl shift, mostly 1,2 alkyl shift, like the group which is present at your 1 and 2 position, to give you imines. For example, your tertiary butyl azide first generates this nitrine, which undergo 1,2 alkyl shift to give you your this imine. Similarly, uh, in this case, your triphenyl methylazide, which is a diazide compound of your acetophenone. So you have two azide groups here, so which can generate two nitrins. So if it generates one nitrin, then it can undergo 1,2 alkyl shift, and then your rearrangement to give you 1,5 diphenyl tetrazole. And if it generates both the azides are turned to your nitrins, then it can undergo some other type of reaction, in which first is your 1,2 alkyl shift, and then insertion to give you 2-phenyl imidazole. So in this reaction you have a rearrangement as well as your insertion reaction. Next is your Hofmann rearrangement, or that is also known as your Hofmann bromamide reaction, or that is also known as your Hofmann degradation, because actually from whenever you have n carbon on the starting amide, you are getting n minus 1 number of carbons. One carbon is less, so that's why that is also known as your degradation. So in this case, this Hofmann rearrangement, when primary amides is treated with your uh, any halogen, mostly chlorine or bromine, in presence of a base and heat it, the product is your primary amine. But its mechanism is, so this primary amide in presence of your base, so that first abstracts a proton to generate this it abstracts a proton to generate say anion on this nitrogen, and now this negative charge, this nucleophile, will react with your bromine in nucleophilic substitution to form a N-bromoamide. So now this N-bromoamide, again it has another hydrogen which is more acidic as compared to this hydrogen, because now you have a minus I group attached to it. So that will take off this proton again to generate a negative charge on this nitrogen, and this nitrogen, from this you can just say this bromine will leave to form you this nitrine, and this nitrine intermediate will undergo actually a rearrangement to form your isocyanate ion. So when you treat this isocyanate ion in presence of your water, actually this will come here, and this bromine will leave to form your this nitrine intermediate. Okay, so this isocyanate ion will react with water to generate finally to give you your amine. In between, one carbon dioxide molecule will be uh, actually displaced or released. So this is starting from your primary amide, you get your primary amine, and here the intermediate is your isocyanate, and also you have a nitrogen intermediate, but you have a very stable intermediate, that is your isocyanate. You would say that this isocyanate intermediate is actually uh, um, being formed in many types of rearrangement reactions. So the next rearrangement reaction is your Cortius rearrangement. So in Cortius rearrangement, the starting material is your acyl azide. So this acyl azide is formed from your acid chloride, acid halide or acid chloride, by treating it with potassium azide. So this is a kind of nucleophilic addition substitution reaction. And so that gives you acyl azide, which is your starting material. So this acyl azide will undergo in presence of your, this is actually formed because this is resonance stabilized. So it would undergo some in presence of your light or heat, that will undergo one elimination reaction where nitrogen molecule is eliminated to give you your nitrine intermediate. So this nitrine intermediate again undergo rearrangement where your R group is going to your nitrogen, and this is coming to your nitrogen carbon bond to form a isocyanate intermediate. This isocyanate intermediate has many fates depending on the reagent you are using. If you use alcohol, then that is going to give you a carbamate. If you use alcohol, then that is going to give you amine, and if you are using an amine, then that is going to give you a urea derivative. So here also, starting from your acyl azide, you first get nitrine, then nitrine rearranges to give you isocyanate, now which can give you many products. So this is your Cortius rearrangement. Then there is another rearrangement, that is your Schmidt rearrangement, where starting from acid you get your amine. So in this rearrangement, starting from acid in presence of your H plus, first it gives you an acy- acylium ion, okay, cation. So this acylium carbocation in presence of your azide, okay, hydrazoic acid HN3, so that gives you acyl azide. So now from this acyl azide, elimination of nitrogen elimination of nitrogen gives you uh, actually this isocyanate, and this from a series of reactions you would finally get your amine. So in this Hofmann, Curtius and Schmidt rearrangement, everywhere you just see that the intermediate is your isocyanate. For example, in case of your Hofmann bromamide, the starting from amide, you in presence of bromine and sodium hydroxide, you are getting isocyanate, and in presence of water, that is giving you amine. And in case of your Curtius rearrangement from acyl azide, when you heat it, nitrogen is removed, that gives you isocyanate intermediate, and this isocyanate intermediate's precursor is your nitrine. So this isocyanate intermediate, if you treat it with alcohol, that gives you carbamate. So this rearrangements proceed through a similar key rearrangement step in which this migration of this group, which is just actually attached to your carbonyl group, that migrates to nitrogen, and your leaving group departs, generating your isocyanate intermediate. So next intermediate is our arine intermediate. Mostly we will deal with your benzene intermediate. So there are in case of your nucleophilic substitution reaction in aromatic compounds actually does not uh, undergo nucleophilic substitution reaction readily as compared to their aliphatic counterparts. The reason is, in case of your aliphatic reactions, the nucleophilic substitution can either undergo through SN1, in which first generation of a carbocation is occur, then your nucleophile will attack, or it can go through your SN2 pathway where your nucleophile attack and the leaving group departs. So that can be either in two ways, SN1 or SN2, depending on your substrate. But in case of your aromatic compounds, so it is very difficult to remove this chlorine group. First of all, this chlorine has three lone pair of electrons, and uh, this carbon, in case of your aromatic compounds, that has a car- double bond character because of conjugation. So this lone pair of electron is in conjugation with this aromatic ring, so that gives you a carbon chlorine double bond, okay, and you have negative charge here, yeah. So it is very difficult to break this carbon chlorine bond as compared to in case of your halogens, aliphatic compound, sorry, aliphatic compounds. So it is difficult to break this one, so no SN1. And again, for SN2 it has to attack from the backside, so nucleophile can't attack from the backside because it has to go through repulsion through this 6 pi electron. So in case of your aromatic halides, SN1 is not possible as well as your SN2 is not possible. So if you just see in this reaction, this in presence of aqueous sodium hydroxide, you have to give very high temperature, 625 Kelvin and 30 megapascal your pressure. So in that case, your nucleophilic substitution reaction is taking place, but still you would just see that this is not going through SN1 or SN2. Rather, if you introduce some um, if you introduce some electron withdrawing groups at ortho and para position, that increases the reactivity. You can just see the reaction conditions actually is getting milder and milder. For example, in this reaction you just see that only just heating it, using water, you get the product. So in the presence of an electron withdrawing group, you would just see that this uh, you can check your literature. In presence of electron withdrawing group at ortho and para position, it undergoes a mechanism that is your addition elimination mechanism. So more the number of electron withdrawing groups at ortho and para position, the rate of reaction actually increases, or you need more mild conditions. But in this case, when you do not have any such electronegative withdrawing groups at ortho and para positions, that takes place at very high temperature. And again, if we just use in this case a very strong base in liquid ammonia, that reactions also takes place. So that means it is not going through this pathway, rather it is going through some other pathway. So that pathway, like you just see this D. In that case, if you just see in case of this orthochlorotoluene, the product obtained is a meta and ortho. Okay, meta and ortho, both meta hydroxytoluene and orthohydroxytoluene. So you get two different products. And in this case also, if you treat it with amide in liquid ammonia, you get orthoaminotoluene as well as your meta-aminotoluene. So this reaction can only be described by the only one intermediate, that is known as your benzyne intermediate. Okay, how this benzyne intermediate is created, we can just check our next uh, reactions. So first is your generation of your benzynes. So in this case, actually in case of your benzyne intermediate, first step is your elimination, next is your addition. Rather in this case, we have addition elimination mechanism for this reaction, addition elimination. But benzyne mechanism is your first elimination then addition. For example, you can get benzynes from aryl halides. So first step is you just take out proton. In case of your very strong base, you can take out this proton, and that generates a negative charge, and this goes here, your X is removed. So first step is your elimination of HX. So, in case of your sodium hydroxide, there you have to use very strong conditions, very high temperature, and amide. In case of your amide, that is a very strong base, so that will be able to take out this proton. Although this proton is not very acidic, very weakly acidic, very less acidic, but still you are using a very strong base, so that can knock out this proton to generate your benzyne intermediate. So not other hydrogens will go, because in that case we are using a base. So among these two hydrogens, here we have a hydrogen, here also we have hydrogens, here also we have hydrogens, here also we have hydrogen, but still this hydrogen or this hydrogen, they are equal. So this hydrogen will be removed because this is acidic. Okay, and also from orthoaminobenzoic acid, so this we have a amine group. If we treat it with nitrous acid, first your diazonium salt will be prepared, and then by removal of your nitrogen, you get a positive charge. Then decarboxylation gives you benzyne intermediate. So even from iodophenyl mercuric iodide, using your flash photolysis method, then also you can get your benzyne intermediate. And also from 1 to dihalobenzenes also you can get your benzyne intermediate. So there are many methods to generate your benzyne intermediate. Next is your structure and stability of benzyne. Okay, all these intermediates, I think you can get one or two questions, like to show the orbital picture, to show the structure and stability of these intermediates. So in case of benzene, like we have a carbon-carbon triple bond on this case, so that is actually like your alkyne. So in this case, we cannot say that this carbon is, in case of alkyne, we have carbon-carbon triple bond. In that case, this carbon is sp hybridized, and both these bonds are p orbitals, which one is be px px, another would be your py overlapping. But in this case it cannot be possible, because here we have all the p orbitals are overlapping, and we have an sp2 hybrid orbital. So here you have very poor overlap of sp2 hybrid orbital. So that gives you a very poor overlap, and that gives you a significant ring strain, because triple bond in that gives you very ring strain. So this is highly reactive. Okay, because this sp2 orbitals, because this is a overlap of sp2 orbitals, two sp2 hybrid orbitals will not be actually aligned for triple bond formation. Next is reactions of arynes. So whenever we have how these benzenes will be reacted. So your first step is the formation of your benzene. So for example, uh, in these two molecules, like in this case we have only hydrogen here, so we do not have any option. So first this hydrogen will be removed and we get this benzene. So that even in this case also this hydrogen will be removed because that is the most acidic hydrogen, so we would get this or this hydrogen, they both are same. Okay, we are going to get this benzene. But in this case we have one hydrogen here, also one hydrogen here. And if this Z group, this is more electronegative, then this hydrogen is more acidic, so this one would be removed. So in that case we would get this benzene, not this benzene. If this is not very electronegative, then this hydrogen will be removed. So first of all we have to check which hydrogen will be removed. The more acidic the hydrogen, that will be removed, because acidity is related to inductive effect of Z. It may be stated that the electron attracting Z favors removal of orthohydrogen, while an electron donating Z favors your removal of your parahydrogen. So if Z is more electronegative, this hydrogen will be removed. If electron, this one is less electronegative, so this hydrogen will be removed. Stability, and next also this depends on the stability of your carbanion formed. So once your benzene intermediate is formed, next is the attack of your nucleophile. So for example in this case, this hydrogen will be removed to generate this benzene intermediate. Now this NH2 would go to NH2 minus, will react uh, either on this carbon or on your this carbon to generate your metatoluidine or paratoluidine. In this case, the both would be formed in equal amounts because we have a CH3 group here. So, for example, this is we can just say this is an evidence, because if we just take one compound where this carbon is, where your chlorine group is attached, we have taken another isotope of this carbon, C14. So now in presence of your amide, so now this NH2 minus can attack the carbon having the port uh, labeled carbon, or the other carbon of other side of your benzene ring. So you can get two different products. So that is actually the product. So this gives another evidence that benzene is being produced in your reaction mixture. Again, another thing is, suppose you label, okay, this is the same one, you are going to get the two products, 1:1. Okay, benzene intermediate, that is going to give you the same product. Okay, I am not going in detail of this one. Suppose in this case we have your orthobromoanisole. So now this hydrogen will be removed because that is more acidic hydrogen, to generate you 2,3 benzene intermediate. So now now the NH2 minus, okay, so now the NH2 minus can attack either okay, the NH2 minus, okay, we have, and in this case uh, we have this meta bromoanisole. This is your orthobromoanisole. We do not have any we do not have any option, so in that case we would generate this carbanion because this hydrogen is more acidic, so that would be removed and then you get your 2,3 benzene. And in case of your meta bromo anisole, you have two hydrogens here. Either this hydrogen will be removed or either this hydrogen will be removed. Actually this one is more acidic, more acidic, so this hydrogen will be removed and then you get this benzene intermediate, not this one. And again, once you have this benzene intermediate, the next step is where your NH2 group is going to be attacked, whether that is going to be attacked here or this is going to be attacked here. So in that case, if it is going to attack here, then this one is going to be the negative charge, the carbanion formed is going to be on this carbon, or if it is going to be attacked here, the negative charge will be on this carbon. So among these two, this one is more stable because this is nearer to your OCH3 group. Okay, you just remember this one, there is no resonance here, that just depends on your inductive effect. So this is a minus I group and presence of your negative charge nearer to it, that stabilizes it. So this one will be formed, the end product will be, next step is proton abstraction to give you this meta amino anisole. So that also depends. So there are two parameters in case of your benzene mechanism. First is your most acidic hydrogen will be removed to form your benzene. Next is the carbanion which is formed in the next step by the attack of your amide, so, should be actually closer to the more electronegative substituent, or that should be more stable. So there are some other evidence, like if you have both the ortho positions nearer to your halogen group is blocked, no reaction would take place. And so that means no ortho hydrogen, no reaction. So that is also another evidence. And again, this here in the last class I have used your kinetic isotope effect, primary kinetic study of kinetic isotope effect. So if we just replace this hydrogen with one deuterium, so it was being shown that with deuterium, the rate of reaction is very slower as compared to the reaction with your hydrogen. So that involves that it is going through a breaking of this or loss of this proton, because that determines the rate of your reaction. So, loss of proton is the rate determining step in this reaction. The slower the rate, in case of orthodeuterobromobenzene, can be explained on the basis of your isotope effect. Next is cycloaddition and ring closure reactions. So, this benzene intermediate can also undergo your cycloaddition reaction. For example, that also gives another evidence. For example, this hydrogen will be deprotonated first to generate this benzene intermediate. Now we have an intramolecular nucleophile is already present here, so that will react here to give you the final product is your N-methyl indolin. And if our reaction in your reaction mixture we add some tetrahydrofuran, so that undergoes 4n plus 2 cycloaddition reaction. So that is also works as a trapping reaction. So uh, that gives you a fused ring cyclic products. So it undergoes 4n plus 2, so this acts as a dienophile. In case of your 4n plus 2 reaction, you have a diene, that is your Diels-Alder reaction, 4n plus 2. So this is a 4 pi system, this is a 2 pi system, so this is your diene plus dienophile. So in this case our benzene reacts as a dienophile, and our this one is your diene, and in this case this one is your diene. So you can get your end product. So this undergoes your cycloaddition reaction. Even two molecules of benzene undergo cycloaddition reaction to give you a three-membered ring here. So this is kind of like 2 plus 2 cycloaddition reaction. It undergoes in a cyclic manner, 2 plus 2 cyclic reaction, or this can also undergo addition to another uh, three more uh, benzenes react with each other to form a four-membered ring. So this can also undergo 2 plus 2 cycloaddition like here with your allyl cyanide to give you this product, or uh, this 2 plus 2 cycloaddition reaction with other dienophiles to give you this product. Okay, so you can just predict the products in the corresponding reactions. You can check the corresponding intermediate in each of the following cases also. For example, in this case, we have two chlorines. So either this hydrogen will be removed or this hydrogen will be removed. They both are ortho and meta to each other. So in that case, the first is your benzene intermediate. This benzene will be produced. Sorry. So first step is the formation of your benzene. So this benzene will be formed. Okay, chlorine. So next step is whenever our NH2 minus is attacking, so this benzene will be formed. So it can attack this side or it can attack the other side. If it attacks this carbon, then this is going to on this carbon, the negative charge, the carbanion formed will be on the other carbon which is nearer to, so this one will be only formed, then proton abstraction from your NH3, and the final product of would be metachloroaniline. And in this case only this hydrogen will be removed because that is more acidic, and in this case there would be no problem whether this hydrogen they are equivalent, whichever hydrogen would be produced. So in this case this hydrogen will be removed to give you the benzene intermediate, then you can also carry out the reaction, and in this case this benzene will be formed, this benzene will be formed, and when your NH2 will react, NH2 minus will react. In that case, it would react here so that the carbanion is nearer to this group, not on this side. In that case, the negative charge would be on the para carbon, which is far from your chlorine group. Then you would get the product. So that would give you your para chloroaniline. Next, last step is reaction with your ammonia, that gives you the final product, protonation. So this finishes your reactive intermediates, also your MCH-012 part. So if anyone is having any doubt, you can just ask me. And the files, like the PDF of these lectures, I will try to send you today or maybe tomorrow morning. I will send you definitely to maybe to Senapati, and I have someone else number. I would send those two persons. Okay.
Ma'am,
So
yesterday's files you have sent?
no. I have not sent. I will send
Okay.
tomorrow morning or today, today night or tomorrow morning. I will send to
Okay.
Senapati or some other girl. She has also sent me the her number.
Okay, okay,
Okay.
ma'am.
Yeah. And if you any of you is having any doubt, you can just ask me. So for organic chemistry, you have to do many, actually, lots of practice. And so, any doubt?
No, ma'am. We have
Oh,
to study first and then
yeah.
we'll get some doubts.
Okay. No problem. So all the best for your exam. I hope you
Thank
will
you.
all do well.
Thank you,
And
ma'am.
yeah, most welcome. So maybe second time or I can we can again contact and get in touch.
Okay,
Okay.
ma'am.
Yeah. So thank you everyone for listening properly.
Thank you, ma'am. Thank you very much, ma'am.
Yeah. Most welcome. Okay. Okay. Good
Good
night. Good
good
night.
night, ma'am.
Yeah. And all the best for your exam. Okay.
Thank you, ma'am.